So I'm Xavier Destree. I've been a long time, I'm still a long-time consultant to the ArcelorMittal company. And a theme that we have been looking at for many years, almost decades, was the structural use of the steel fiber reinforced concrete. Now I'm going to comment on the 544.6R-15. That is a design report on how to design steel fiber reinforced concrete suspended elevated slabs. That means with almost a total elimination of any traditional rebars. So it is seen as the ultimate step in the structural activity. First of all, this is nothing new. It has not been done last year. No, it's the first structural applications were indeed piled slabs. As you can see, I don't know if you see here, ground slabs sometimes are over piles, built over piles. And since 1992, this application has been used with steel fiber reinforcing only massively. We have today probably at ArcelorMittal 15 million square meters of reference existing like that over the 5 continents. And then later on, you can see that at the right picture, the next evolution, that is, it was started at the design research and in practical research back in the year 2002. I remember we had lots of testing being organized at the Polytechnic of Montreal with Professor Massicotte. And then it was decided to have full-scale tests on that. So finally, the first one to be built was in 2004. Right now, there are over 100 buildings that include suspended elevated steel fiber reinforced concrete as only reinforcing. A few examples of full-scale tests that have been conducted. I must say that between the year 1993 and today, there are more than 12 different full-scale tests that have been organized in a very well scientific organization with universities and third parties. The slide here shows a full-scale test on an elevated slab in in Australia, where it was decided to check, investigate by some customers there, that a slab, what could be the loads carrying ability of a slab spanning 3.10 meter by 3.10, a slab of 160 mil thickness with 45 kg per cubic meter of steel fiber. That was organized by the local university, the James Cook University in the New South Wales state in Australia. And indeed, what we can see here is that the difference between the first flexion crack and the ultimate load was a factor of 5. So it's a huge ductility that was available. On the next slide, this is another full-scale test where there the span was 6 meters. You can see there was a set of 16 columns with a column width of 6 meter by 6 meter and a slab of 200 millimeter thickness, with, in this case, with 100 kilogram per cubic meter of steel fibers. And this has been tested against point loading at the center span, the corner span, the edge span, in service condition and up to ultimate. And there again, it was observed that there was about a factor 5 to 6 between the first crack and the flexion and the ultimate in many cases. You can see in the bottom, the photo in the bottom, that is the kind of deformation at the total ultimate stage that was achievable at the corner span. You could see, first of all these yield lines and multiple cracking, and also that the slab is still able to undergo almost a 200 millimeter deflection at a residual load that is still higher and larger than the first crack loads, just to show how much ductility was available. Another test that has been organized in Estonia, in Tallinn, And that was also for a suspended elevated slab of 5 meter span and a slab of 180 millimeter. And it was again tested for point loads and UDL, and the cracking was investigated in detail. And you can see here, that's quite interesting. You can see here under the central span, the center point loading here at a loading of 250 kilonewton, which is 25 tons, for that slab of 18 centimeter thickness. You can see the kind of cracking pattern under the positive moment that we had. And this loading of 250 kilonewton was needed to cause the 0.3 millimeter cracking that is in the Eurocode, the typical crack opening that is the limit for a reinforced concrete. But here we are at a load that is probably almost 30 times higher than the service loads that the slab would have been sold for. So you see again there's a huge ductility. It is so far that at the almost ultimate load of 60 tons, we had still only cracks of 3 millimeter opening. That corresponds about to the crack opening that we have in the standard flexion test, like the Euro norm 14651 or the ASTM 1609. To get up to that kind of cracking, we need to have loading intensity applicated that are something like almost 70 to 80 times the real commercial load. This has been further investigated in other cases of full-scale tests where we came all time with this same conclusion of the very high ductility, that the cracking limit of the slab was enormously smaller than the ultimate loading, and that this is totally reproducible, as we have been conducting testing on several continents with different concrete. In some of them we were not even personally involved. So I think this is one of the reasons why it was decided about 10 years ago to start to prepare that 544.6R-15 documents, together with the considerable practical experience on job site with satisfied customers. Now I'm going to be more precise about the document itself. And one first very important provision for at least the elevated slabs, it is that we will require a minimum amount of continuity rebars. That is fundamental. And what are these rebars? They are also named anti-progressive collapse. That is known, it was I think known first in the Canadian standards in 1992, and that's where we picked it up from. So that this provision is such that it recommends to install bottom rebars going from column to column very simply and along the perimeter. And these rebars have the function of keeping the slab suspended in case of the disparition of one or more columns. Of course, there'll be a huge deflection, and we have even tested that in reality. But the slab would not collapse, and then the progressive collapse would be stopped. Now, regarding the calculation of these rebars, we'll show examples later in this presentation. But the idea is quite simple, that these rebars are designed just like cables that are supposed to carry the dead weight of the slab plus the service load. So it's quite a simple design equation that we'll look at. Now what I would like to do is to give you almost, I hope that there are engineers, I guess structural engineers in the room here, but I'd like to give a numerical simple example to show you how simple it is. And I think that's a great advantage of the ACI 544.6R-15. First of all, let's take a typical slab of 180 millimeter thickness, as you can see here, 180. And now we are going to follow exactly what Barzin told us earlier this morning, derived from the stress strain analysis. So we need to know first what is the compression strength of the concrete. We took here what is quite regular and usual, a 30 MPa concrete, giving 37 on cubes. And then from that, we need to derive the tensile strength of such of a plain concrete, which can be done while we can use the standard expression of the tensile strength of the plain concrete. And then we come up to a ratio omega between the compressive strength and the tensile strength of the concrete. For most concrete, this ratio ranges from 8 to about 12, and depending on what the concrete is exactly. So that's a first point. A second point, now we have to concentrate a bit more on the fiber reinforcing itself, and essentially what is the capacity of the steel fibers to give a post-cracking strength, that is to obtain the ductility and that we need in any structural elements. And there, let's start, for instance, from the EN 14651 standard with the notch beam specimen, where FR3 is with a crack mouth opening of 2.5 millimeter. And we have in our case here a typical concrete, fiber concrete, where the crack mouth opening of 2.5 millimeter would require like a 6 Newton per square millimeter strength. That is typically obtained with, in general, by a concrete containing 65 kJ per cubic meter of a 1 millimeter fiber of high strength, 60 millimeter long, and provided with hooked hands. And these data result from thousands and hundreds of testing results that we have had on several sites. Then now we need to focus on the mu factor. If you remember, Barzin explained us that two factors were quite important to start to build up the stress strain diagram. It was the omega factor and then the mu factor. And the mu factor is simply the ratio between the tensile in uniaxial tensile strength of the plain concrete and the post-cracking tensile strength of the concrete under uniaxial condition. And the ratio is mu. So if you divide, in other words, if you divide this value here by this one, you can obtain mu. Mu for the steel fiber reinforced concrete with sufficient ductility, in general, values start like around 0.35 to 0.4, and with probably the most performing steel fiber reinforced concrete for structural purpose, we can reach like 0.8 at most. So in our cases, with a omega of 10.35 and mu of 0.67, then we come up to the expression of the design moments of the fiber reinforced concrete. For our slab of 180 millimeter is showing a design resisting moment of 29 kilonewton meter per meter. You could now make a calculation with rebars, and to see how much rebar you need to get that, it's quite high. So it's a very effective, quite an effective design method. Well, that was for the resisting. Now we are on the design moment indeed, and it is using the yield line method, so that the slab is being divided into yield lines under the loading, and the yield lines we select the shortest pattern possible between the columns, so that we use the straight pattern, and there are three cases for the interior panel, the edge panel, and the corner panel, which is simply to take the total loading of the bay divided by 8, 12, or 16, with the important remark that the span is taken as a net span, because the position of the yield lines is also a function of the size of the columns and the thickness of the slab. So we come up here, all calculation made with the factored loading. We come up to a design moment of 20 kilonewton meter per meter, so that we have a ratio of 0.7 almost between the resisting, between the design and the resisting moments. I think something that we have taken here is phi p equal to 1. I think, well, generally 0.9 is recommended, but okay, it's 0.8. So this is now a quite interesting diagram where we have summarized lots of fiber concrete test inflection in function of the curvature and the moment or deflection stress. And we have here the diagram for a small prismatic specimen, notched or not, where we can see that, say that we have the first crack, say at around 5 Newton per square millimeter, 5 MPa, and then a post-cracking, okay? And then the curvature, we can see what's the value of the curvature. Now, we can also have in these, in that diagram, we can have also all these full-scale slabs that have been tested, you see? So, of course, as we were saying, that the ultimate load is at a moment that is about 5 to 6 times the first cracking load. You see that after 5 MPa, we have quite a huge post-cracking diagram where the curvature, in many cases, do not even reach the curvature that we have under the Euro notch specimen at FR3. So the FR3 curvature is probably more than anything that can happen in reality in a structural slab, even at collapse situation. And now the numerical example that's of the slab of 180 millimeter, under the loading that we have been using in this case here, we were at the flexion stress under unfactored loading at 2.68 Newton per square millimeter. So you see that according to the ACI 544.6R-15, this triangle here, it is indeed the domain of utilization of the slab. And so you can compare the area of that triangle with the real area of a real full-scale slab. And so you understand how safe it is. But now figure out that there are some other document, like in Germany, where they are so negative and so backward against fiber concrete that you would end up in a triangle that it is almost 1/3 of what we could have with ACI 544.6R-15. And indeed, in this case, the fiber concrete is simply eliminated. They'll be with rebars forever. Punching out is not critical as long as you have like a span to depth ratio that doesn't exceed 30, 32. It has never been critical. Deflection loads are indeed not as high as the punching load. So we have done lots of punching tests and it's never critical. This can be calculated using the 6R-15 equations. We derive that again from mu sigma CR with a 0.66 coefficient that is typical to 318. And then we come up to the safety, the final safety between the reaction on the column and the resistance. I'm done. I'm almost done. The last calculation is regarding the anti-progressive collapse rebars, where again, this is for a 5x5 column grid with a 4 kilonewton per square meter loading. And then we have to sum up the load of the live load and the own weight. And then we simply sum the total weight that is divided by the tensile strength of the steel bars. And we come up here with the section of the APC rebars. In that case, could be 3 rebars of 12 millimeter bottom running from column to column and around the perimeter. The deflection, there is also a rapid formula to calculate the deflection. We end up with 2.6 millimeter with our numerical example. This has been compared with a real example of the same span and same thickness, where under 5 kilonewton per square meter, we had only 2 millimeter deflection. So indeed less than what is calculated. And then there are practical cases that are demonstrated, buildings that have been built. You can see here the APC rebars. Yeah, case. You see, concrete is rather self-compacting. And again, I think Amir shows that photograph already. This is a tower in Estonia that has been completely built with steel fiber concrete from the raft to the roof. And that is an arena in Stockholm, 25,000 cubic meters of fiber-reinforced concrete, where the raft was a piled raft. You see all these small black points are piles, and that was with the steel fiber-reinforced concrete at 50 kg dosage rates. And then raft foundations, we use the resisting moment equation of ACI 6R-15 to use it as the resisting moment for raft foundations as well. Thank you.
Thank you, Xavier.